All right, let's jump straight into it. Welcome to this detailed explainer where we're tackling a massive, everyday headache for clinicians, professionals, and students alike. And that is, how do you quickly and honestly, ruthlessly filter out low-quality scientific studies? I mean, we've all been there, right? Staring down a towering stack of papers, wondering where to even begin, and just terrified of wasting our precious time on bad science.
Have you ever felt completely overwhelmed by the sheer volume of scientific literature that gets published every single day? It's a very real struggle. You sit down, fully intending to do some solid research, and immediately that fear creeps in. What if you waste an entire hour trying to decipher a horribly constructed paper on some new therapeutic, only to realize by the end that the data is essentially meaningless? Your time is incredibly valuable. Spending it on flawed science isn't just frustrating, it's hugely inefficient.
Well, let's dive into a genuinely brilliant solution for this, the Evidence-Based Veterinary Medicine Association's QUIT tool. We're talking about a highly practical 10-question checklist that is specifically designed to instantly triage research articles. It's a structured, detailed way to assess whether a paper actually deserves your attention. It essentially gives you a roadmap to either proceed with confidence, proceed with caution, or just stop completely.
So here's how we're going to break things down today. First, we'll look at the reading time dilemma. Second, introducing the QUIT tool. Third, abstract and intro deal breakers. Fourth, methods, the yellow and red lights. Fifth, we'll look at results and those crucial numbers. And finally, discussion, limitations, and conclusions.
Okay, part 1, the reading time dilemma. Too many papers, too little time. Moving into part 2, introducing the QUIT tool, which is basically your new X-ray vision.
Look, time is that one resource we can never, ever get back. So we need a systematic, highly efficient way to know what to read and what to literally just toss in the trash. Now, while this specific tool hasn't been formally validated in the literature just yet, its true power lies in its detailed logic. It gives you a crucial red light, green light framework for your reading process, letting you scan a paper almost like you have X-ray vision. The stakes are clearly defined. Answer yes to the tool's questions, you get a green light. That means, yep, invest your time to consider the paper thoroughly. But a no answer acts as either a yellow flag for a potential concern, meaning proceed with caution, or a bright red light. A red light means a serious concern is present. It's a hard deal breaker, and you stop reading right there. What's really brilliant about this checklist is that it naturally follows the flow of a standard scientific paper. It's structured around 4 main sections: abstract and introduction, methods, results, and finally, discussion, conclusion, and limitations. So we're going to do a detailed chronological walkthrough of this tool, mirroring exactly how you'd read a paper from start to finish and applying that X-ray vision at every single stop.
Let's hit part 3, abstract and intro deal breakers, the first hurdle. Let's start with the very first section of any paper you pick up. Question number 1 is your ultimate gatekeeper. Based on the abstract, the tables, and the figures, are the outcomes actually clinically relevant to you? That's the crucial point. If they aren't relevant to your specific clinical questions or your field of practice, it is an immediate red light. Stop reading. There is zero reason to spend an hour dissecting the detailed biochemistry of a drug if the clinical outcome has absolutely no bearing on your day-to-day work.
Building right on that, question 2 checks if the study compares different groups. Failing this, another hard stop. If there's no comparison group, like say a control group versus a treatment group, it is incredibly difficult to prove causation or efficacy. So if the answer is no, red light. The paper simply isn't worth any more of your time because its foundational design can't answer complex scientific questions.
Moving on to part 4, methods, the yellow and red lights.
Okay, assuming a paper passes the intro phase, we wade into the dense stuff, the methods section. Here we're ticking through some vital methodological criteria. Question 3. Was a sample size calculation done? If no, yellow light. The study might be statistically underpowered. Question 5. Did researchers actively assign subjects and treatments to groups, avoiding pre-existing groups? A no here warns you of potential selection bias. And question 6. Were subjects assigned randomly? Skipping randomization is a massive caution flag. But hidden right in the middle of these is question 4. And honestly, it is an absolute trapdoor. Let's isolate that trapdoor for a second. Question 4 asks, are reporting guidelines followed, or at the very least, are the methods and outcomes described in enough detail for you to understand and for the study to be replicated? If a study cannot be replicated, it is bad science, period. If they're hiding their methodology or it's just way too vague, hit the brakes and stop. Massive red light deal breaker. Do not waste your time guessing how they did the work.
All right, part 5, results, the crucial numbers. So the methods look solid.
Next, we advance to the results section to see if the actual data holds up under scrutiny. For question 7, we're asking, do the authors report results for all the outcomes they just described in the methods? You'd be surprised how common it is for researchers to measure 5 things, but only report on the 3 that gave them exciting results. If they fail to report all their predefined outcomes, glaring yellow light. Proceed with serious caution, because you might be looking at a heavily filtered, cherry-picked version of the truth.
Which brings us to question 8. This is a hard, screeching halt. Was the group size, the n, equals, for each group, and a variance metric like standard error of the mean, standard deviation, or confidence interval explicitly reported for every single outcome? An average means absolutely nothing if you don't know the spread of the data or how many subjects were actually tested. If they omit this detailed data, drop the paper immediately. Red light. Finally, part 6, discussion, limitations, and conclusions. We've reached the end of the paper, and now it's time to evaluate how the authors interpret their own work. Question 9 asks a very simple but telling question. Do the authors discuss their study's limitations? Look, no study is perfect. Every single piece of research has flaws, constraints, or alternate variables. If the authors skip this vital self-reflection and present their work as completely flawless, that's a huge yellow flag. Good scientists know and admit their boundaries. And here is the ultimate deal breaker. Question 10. Do the results actually support all of the conclusions? Sometimes an author's summary goes a bit wild, making grand claims that their actual data just doesn't back up. If the reported results do not strictly and logically support all of their written conclusions, the paper fails the test entirely. Red light. You can confidently disregard their final arguments. All of this leads us to a final, pretty provocative thought. If a published scientific paper fails the very basic logic of the QUIT tool, if it lacks clinical relevance, hides its methods, omits sample sizes, or makes unsupported claims, why was it published in the first place? It really challenges the whole peer review process, doesn't it? But for now, you have the power to fiercely protect your reading time. Use this detailed checklist, demand better communication in science, and never waste another hour on a red light paper.